Good morning. I'm surprised to see this many people with their eyes open. So, welcome to my talk. This is called Racing the Web. And I'm going to give you some forewarning. There's a lot of content here. There's a lot of stuff that I want to go over. So I'm going to be flying through a few of the sections, but if you pay attention to my Twitter profile, I'm going to post the slides after, shortly later on today. So you'll be able to go over the stuff in a little bit more detail. But try to keep up. Hope you got your coffee in hand because I'm going to go really quickly in some parts. So stay with me. First off, this is me. My name is Hnatiw. You can find me on Twitter at Inspector. I'm a security consultant at Security Compass. I'm also a professor of application security at Georgian College in Ontario, and also a software developer. Formerly I did it professionally. Now I just do it for a hobby, and former sysadmin and a lot of other things. But that's what brings me to the stage, and why am I here talking to you? So I am here today to talk to you about something that is the plague of many developers over the past, 20-some years, ever since we had multi-threaded CPUs, and ever since we had the capability of doing things concurrently. This has been the bane of many developers' existence. So let me begin by telling you that I'm here because I want to go fast. So I'm going to talk to you about race conditions. Now, race conditions, there's even an OWASP definition. I won't read it to you because you all, I think, are capable of reading. The key here, though, is that bottom point, race conditions by their very nature are difficult to test for. And I'm going to show you why. And this is why a lot of people don't really know about them, because they don't really see them, or if they do see them, they think, oh, it's just a fluke, and then they ignore it. So moving on to the next slide, there's also a CWE for it. And what's interesting about the last one, going about the OWASP definition, when you talk to developers, the developers come up and ask a lot of us in the security industry, I'm developing this web application, or I'm developing X, and I want to make it secure. What do I do to make it secure? Oftentimes what we'll do is we'll point them to the OWASP top 10. Pretty good standard way to get a basic understanding of what are the top things that you should be looking out for as a developer when you're writing a web application. So the race conditions are not actually on the OWASP top 10, but they are just as important. And if you go to OWASP, there's a lot of other really important issues on there, but I'm going to highlight this particular one. So a race condition is concurrent execution using shared resources with proper synchronization. That's the CWE standard definition for it, but really, it's when you're betting on the wrong horse or even betting at all. I'm going to describe a little bit more detail what that means. So many people in here probably aren't developers, don't have a development background, so I'm going to try to get it across to you, get that point so that you understand what it means, not necessarily at a detailed technical level, and then we'll kind of go a little bit deeper from there. So let's start with pictures. So taking a look at this, we have two processes here. These processes can also be a function or an operation. Doesn't matter how you look at it, but they're two different things that need to happen at the same time. First one, process X, has 4 steps. Process Y has 2. Typically, process Y is going to finish first because there's only 2 in it. Doesn't take as long. Oftentimes, that's the assumption. This one's always going to finish first. So we make that assumption based on a pretty obvious facts that we have in front of us. But if we're not prepared for it, that assumption can really shoot us in the foot when process X actually finishes first. That's a race condition. So a race condition really is when you're assuming that we have multiple tasks going on at the same time. We're assuming that there's an order. One thing's going to happen before the other one. When the other thing happens first, it can be rare when that happens, but when it does, that's when you get a race condition. So essentially, that's what it is. Oftentimes, this really becomes an issue when you're dealing with shared resources. So if you're dealing with data from a database, or you're dealing with a file access, if you're assuming that one process is going to finish using it first, then the other process is going to use it, but instead it happens the other way around, the results are that oftentimes that data is going to be corrupted or damaged, or some other way it's going to mess things up completely. And that is the result of a race condition. And one interesting fact about this, even in multi-threaded environments, when you're dealing with multiple tasks happening at the same time, oftentimes, let's say you do have 2 or more cores on your CPU. Most programs aren't actually going to be using 2 cores at once. Most of them are just going to be using 1. They're going to be using one thing at a time. So by that very nature, they can't actually do things at the very same time. So what they'll do is the compiler or the actual the process that's running it, the engine behind that program, is going to try to do some tricks to make it look like it's doing things at the same time. So in this case, it'll run process Y, and process Y, that first thing may be taking a little bit more resources, so it'll rapidly switch over to process X. But then all four of those different execution points, all those different things that it needs to do in process X can finish really quickly. So it'll be like, oh, well, I can finish that really quickly, so I'm going to do that, and then I'll hop back to process Y. So behind the scenes, a lot of our programs are doing these things that are trying to optimize how it runs multi-threaded applications realistically in an environment where it can't do that concurrently. It will try to do these things for you behind the scenes, and if you don't know exactly how that works, then that's when you run into race conditions. Even if you do know how it works, it sometimes seems like magic and you can't predict it. So next question is, when does this actually become a security issue? So yes, it's an annoying bug. It's something that can cause crashes in your program, and it's not at all that pleasant, and it's, like I mentioned, really, really difficult to test for. So when does this actually become a security issue? So it's not just difficult to test for, it's not just a bug. It also is a security issue, especially when you're dealing with sensitive operations or you're dealing with financial details. So let's get to the first example. So if you're dealing with one-time use coupons, if you get coupon codes, they'll be maybe automatically generated to give you a discount on like hosting or on a product or something when you're shopping online. When you're using these coupon codes, oftentimes, if you look at the process of how it uses those coupon codes, the order of operation is check if the coupon code is used first. So it's got the coupon code after it's randomly generated it, check if it's used, apply the coupon code to the account, and then remove the coupon code from the database. So those are 3 steps that you assume are going to happen in order, in that very same order. And most of the time it will. But what happens if one of those things happens out of order? Well, if that happens out of order, then it could just be that that coupon code doesn't apply or it gets removed and then you lose your coupon code. But another way of looking at it is, instead of it just not happening in order, what if because you have many different people trying to use that at the same time, let's say someone sends a lot of requests trying to use that coupon code, what if that second step of applying the coupon code to your account happens many, many times before it actually removes it from the database? In that case, your discount will probably become significantly higher, and that one-time use coupon code doesn't become a one-time use coupon code. And in that case, you could, if there's not the proper checks in place, it could end up with you getting paid for buying a product, or you get a significant discount on that product. So this has happened many times. This is just an example from Newegg. I don't even know if it's happened on Newegg, but it's been happened on hosting providers. It's happened on other product websites. If you don't make those proper checks, that's what can happen with a race condition. Let's look at the next one. Bug bounty payouts. This actually happened. If you look at it's at the very bottom, hard to see, but there's a link there to a Cobalt.io bug bounty report where they actually submitted a bug bounty report to that website, and it got approved, and they got paid out in Bitcoin. But when they did the payout, what they did was instead of, so that order of operation is check the database for the bug bounty payout, send the money to the researcher, and then mark the payment as complete. So those 3 things are supposed to happen in order. But again, if those things happen out of order, or what happened in this case is if that second step happens a bunch of times before that third step happens, they send the money to the researcher a whole bunch of times before marking that the actual payment has been completed. The researcher ended up with thousands of dollars on top of what they were supposed to have gotten for that bug bounty payout. They got another bug bounty reward for submitting that bug bounty reward. So that's just an example of a race condition when you're dealing with money and you're dealing with payouts. So making that assumption that those 3 things are going to happen in order, just those 3 things on their own, if you don't have the proper checks in place, that's an example of what can happen as a result. Last one, if you look at video games, mobile games, anything where you have an account where you have some sort of money or credits or gems or whatever, this is an example from EVE Online. It's known as like the world's biggest accounting and economic simulator. It's an interesting game, but you can transfer account balances between accounts. So take the example of one person A sending some kind of credit to person B. The assumption is that the operations that are going to happen is you get the account balance from account A, get account balance from account B, update account balance in account A, update account balance in account B. So it's not necessarily that magically this money disappears from here, shows up here. There's steps to doing that. And so you make an assumption that those steps are going to happen in order, and it's going to happen once. But again, if you were to make those steps happen out of order, or put a lot of load on it and make those, for some reason, like the process pulls down, like finishes process account B instead of account A, what that could result in is if you, for example, get the balance from account A a bunch of times before updating the account balance, that could result in essentially getting money for free in account A, and account B loses less money than it actually should. And I'm going to show you an example of what that looks like soon, but suffice to say, if you're trying to transfer account balances between accounts and you do it really, really quickly, oftentimes if they don't have the proper checks in place, you put it under the proper load, you could get a lot more credits for a lot less. So what does a race condition actually look like? Kind of like this, with the turtle finishing before the hare. But let's take a look in actual code. So I'm going to show you an example in Python. This is a very contrived example, but this is to kind of get shortly to the point to understand what it looks like. In this case, what it's doing is it has a global variable, and it's just in a separate thread. It's pulling down that variable, updating it locally, and then updating the global variable. So it's saying it's pulling down in this use increment thread, it's pulling down a variable, and it says, okay, it's 0, I'm going to add 1, and then I'm going to update the global variable. The global variable is now 1. Does it 50 times, but it's doing them all at the same time. So what's happening is every time it pulls down that global variable, it holds on to that value. But while it's holding on to that value, before it updates the global variable, another process is actually grabbing the global variable before it's been updated. So I'll show you what it looks like, actually. I'll actually show you the code. So that's the code. Let's pull up the terminal here. There we go. I wish I could see this. Okay. Let's see. Python. Okay, so we're going to show it what it looks like. What should happen is it's doing 50 different threads, updating from 0 to 50. The end result should be that the value is 50. Can I make the text bigger? I believe I can. There we go. Can we read that? Yeah. Good. So if you take a look at that, it's easier to see on that side. The account value at the end should be 50, but it ends up being 43. Because if you see in a few cases there, if you look at, let me see if I can show you here. See these two cases here where the value after increment is the same number? That's because it's pulled down that global variable before it was incremented from the previous thread. So they're both pulling down the exact same number, and you're assuming that they're going to pull down the next number, but they're pulling down the exact same one. So the end result is that the value becomes 43 instead of 50. So it's a very small example, but I want to get the point across of this is at the very smallest, most simple level. This is what a race condition looks like. Is we're making an assumption that they all pull them down in order and update them and add them in order. The end result is it ends in less total value. So let me go back to the slides here. So that's what it looks like in Python. So not many people here have probably heard of it, but there's a language called Go designed by a bunch of engineers at Google. It's fairly new. I love it. I use it all the time. It's really useful for distributed systems. It's very lightweight, and it has concurrency built in, and you can compile it across all the major CPU architectures now. It's really useful. So I just wanted to give you an example of what it looks like. This is essentially the same thing, just written in Go, pulls down the value in a separate thread, updates it, and the end result should be 50. I can show you the demo, but again, I don't have much time. Just believe me when I say it doesn't end up in 50. So those are two examples in languages that support concurrency in them. So it supports threading in Python, and it has concurrency built in Go. But there's another example that I want to show you that catches a lot of people by surprise, and this is where you'll find a lot of race conditions. So surprise, it actually exists in PHP. Now, PHP itself is not a concurrent language. It's not built for concurrency. It doesn't have threading like it. It's not a feature of the language. But the language itself doesn't support it. However, the platform that it runs on, if you look at Apache or Nginx, you have to support hundreds, thousands of concurrent connections at the same time on that server. And so the underlying technology of Nginx and Apache, they support concurrency. And so because PHP is running on that, by, I guess, through proxy, by proxy to Apache and Nginx, PHP supports concurrency. So a lot of PHP developers don't think that way because the language doesn't support it. But if you do things like this, which is, in this case, it's reading the data from a database, it's doing something with the data, and then it's going to update it and add it to the database. If during that time, while it's updating the data, and the data has been already updated in the database, that data becomes stale. Now, in this case, this could be, I just use a arbitrary example of view count, but this could be anything. And so what you're making the assumption with in this code is that the data that you have locally is the true data. That's the actual value that's in the database at all times. But realistically, while you're holding onto that data, someone else could be connecting in, and the data could be pulled down on another instance, and those are two different values when you're assuming that they're the same. So is everyone with me so far? Is there, I think that what we've gone over so far is a basic understanding of what a race condition looks like, both in different languages and in a case where you don't really expect it, and kind of the impact on security. I've showed a few examples of seeing how it can impact companies financially and where you can find that. So that's all well and good. This is what a race condition is. But next question is really, how do you actually test for a race condition? And no, it's not double hacking on a keyboard like in NCIS. You don't just type really, really fast. The actual way of testing for race conditions is usually the best way, and this is similar to a lot of different pen testing, the best way to do it is through a white box method because you have a better understanding for the code behind it. And this is very heavily reliant on code. So you identify all the shared data. Then you identify where that data is accessed across systems, find out where the data is accessed is not synchronized, and you just make a ton of requests. So the reason why shared data is so susceptible to this is because you're assuming that the data that you have is going to be the actual value that it should be. So you're pulling data from a database, for example. You're assuming that the data that you have locally is the same that's in the database. But meanwhile, if you're doing something with that data and it changes in the database, you have two different values when you're assuming it's one. So that's why you look at a lot of shared data. So that's the typical way of doing it, but there is a better way. This is where I'm going to show you a tool that I've written called Race the Web. This tool itself is a tool that automates race condition discovery. It uses TOML, so it's Tom's Obvious Minimal Language. It's kind of like YAML, but it's written by Tom Preston-Werner, creator of GitHub. It's just I found it easier programmatically to actually parse through it, and it's pretty easy to read and understand. It's also open source. So I'll show you the source code later. I'll submit it, put it up. Everyone can use it. And cool thing is it's written in Go. So if you want to check out what Go looks like, take a look at that. It'll give you a bit of an intro. Demo time. Awesome. So I'm going to show you what the tool actually looks like. Let's see here. I wish I'd mirrored screens. Okay. Pull this one up. Okay, so this is a website called racetheweb.io. This is an example I wrote up. This will be accessible after. You guys will be able to check it out. What it is it's a arbitrary banking website called Speedbank International. What it does is when you initialize an account on there, it'll give you $10,000, 10,000 credits, however you want to look at it. And what you can do is using the tool, you know what I'm going to show you. Let me just show you. Initialize an account. Once you do that, boom, you get $10,000. Awesome. Now, here's where you have the chance to actually withdraw cash. So let's say I want to pull out $1. Withdraw, what happens? Boom, it dispenses $1. I've just gotten $1. This balance is now $9,999. Makes sense. Now, what I'm going to do now is actually show you how you can exploit a race condition in this code. So first off, I'm going to pull up this. I'm going to make this bigger so I can read it. Okay. So this is the configuration file. What we're going to do is we're going to send 100 requests. We're going to have verbose logging to this one target. We're going to use a post request because this is what you actually need. So I'm not actually going to intercept the request for you because, again, not much time. But suffice it to say that when I make a request to that page saying I'm going to take out $1, it posts to the /bank/withdraw URL, and it passes in a body of amount equals 1. So amount equals however much you want to withdraw. So I'm going to do that exact same post, and I'm going to pass in a different session value. So let's go back to the page, grab my session cookie. There we go. Perfect. And we'll pull it in here. If I can read the session ID. Okay. Great. Session ID value is in there. Okay, so this is what the config file looks like in Race the Web. Pretty straightforward, easy to follow. You can actually add multiple targets. So in a lot of cases with race conditions, sometimes you actually have multiple endpoints you have to do in order, or you have, in the case of transferring account balances, there will be 2 things you need to do at the same time. You can do that here too. This is just, in this case, you only have 1 target you need. So let's quit. Great. So let's see what this looks like. Race the web, and we're going to pass in config.toml. Awesome. And I'm going to actually output to a file so we can review it after. Output.text. Ready? Let's go. Okay, so it's making 100 requests to that endpoint right now, and it's going to output it into output.text, and we'll review it afterwards and see what that actually looks like. Cool. Just finished 100 requests. Let's take a look at the output. So if you can see, it's verbose output, so it actually shows you everything that it's doing. It did 100 requests in 27:52, 8 seconds. Yeah, did it in 8 seconds. Great. The faster you do it, the better it is, because the more chance you have of actually triggering that race condition, because it could happen in like a split second. So the key to doing this kind of testing is you need to do this really, really fast. Because by their very nature, to trigger race conditions, you have to be faster than that actual condition to happen. So it's done those requests. We get a bunch of responses. Here's one of the first responses. So if I scroll down, can anybody not read this screen? Good. Okay. Scroll down. This is the HTML for the page. That's fine. You've successfully withdrawn $1. Wonderful. Our balance is now $9,998. Exactly what we expected. So if I keep scrolling down, shows the end of the page, and it shows, oh no, this is the config in the page, still HTML. Here we go. So there's 0 similar responses from the server, which is what we would expect for that case. Now let's take a look at the next response. Scroll down a little bit. We see that you've successfully withdrawn $1. Wonderful. The balance is exactly what we would expect. And go to the bottom. And now here's the key. In this case, Race the Web actually does a check against all the different responses to see what was unique. So it looks for unique responses. In this case, we wanted them all to be unique because we want the balance to be different every single time. But in this case, there's one similar response, which means it's the exact same response to this. So there's another case where we got $1 out, but the balance was the exact same as this one, which shouldn't happen. So let's scroll down a little bit further and see if we get any more of that. We've got $1. That's great. It's now $1 less. And there's 4 similar responses. So now we've gotten roughly, I guess, $4, $5, $6 out, and it's only $2 down. That's not bad. It's a pretty good discount. Now let me go back to, that's their output. Let's take a look at the balance. If I go back to this page, now the balance we did 100 should be 9,899, right? Let's take a look at what it actually is. We just got $100 for the price of 5. Awesome. So that's just an example of what a race condition looks like, and using the tool Race the Web to actually test for that race condition. So in this case, we didn't really need to have the source code. We didn't have to identify any shared resources. We didn't have to, well, we did have to make a ton of requests, but we didn't have to actually look at the source code to find that. All we had to do was identify that we were making a post request, some basic processing was happening locally, and it was using a remote database. So we just made a whole bunch of requests, and we saw what happened. The response was not what we expected. So this was an instance of a race condition. Awesome. So let's go back to the slide here. There it is. So this website's online for all of you to try out. Anyone can try it out anytime. That's fine. It's got instructions on the page how to use it with Race the Web. Go to racetheweb.io. Now, you notice that on that site, there was a bank application. If there's enough interest in this, I can write other examples of race conditions instead of just like a bank account pulling from that bank account. I want this to be up and available for people, not just for attackers to see how this works, not just for students to actually study this topic, but also for developers, because one of the best tools for teaching developers how to develop secure code is to actually show them what it looks like when they have insecure code, so they can see cases where, okay, I know that this happens when I do this. This is not good. Let's find ways to prevent that. So if you use this website, it should give you an example of, as a developer as well, what it looks like to see race conditions and what the impact can be. So I'm not going to go into too much depth here because again, not very much time, but Burp Intruder is the only other tool that I found that's currently maintained that does similar functionality. It wasn't built for finding race conditions, but it allows you to send a bunch of requests simultaneously. And you can kind of tweak it in ways to make it more ideal for testing race conditions. So I did a comparison versus Burp Intruder. I have some stats on the next couple pages. This is with 1.709, 1.710 just came out, and it's Burp Suite Professional. So it doesn't actually, the problem is if you use Burp Suite Free, Burp Intruder actually limits the amount of, it basically throttles your requests in Intruder, so you can't use it for race conditions with Burp Free. But with Burp Professional, they don't do that. I'll go over speed. I'll fly through the couple slides there coming up, but basically, Race the Web is actually faster by a fair amount, and then also not only is it faster, but one of the key things about Race the Web that makes it different from Burp Intruder is it does that unique response comparison. So if you're doing a black box test against an application and you don't necessarily have the source code, you're not sure whether there's a race condition there, you just want to check to see if something is off. It does that unique response comparison that will show you, okay, if you expected everything to look the same and you have a bunch of unique responses, that's probably not good, and vice versa. So that actual functionality in the tool, I think, is really what separates it from Burp Intruder. Not to say that Burp Intruder isn't great. Burp's awesome. It's kind of like the de facto standard for testing web applications. But in this case, this is the only other tool that I found that kind of does a similar functionality to Race the Web. So that's a comparison. That's how it stacks up. I'm not going to go through this. This is how I'd set it up. Here's Race the Web setup. Yay, there's a difference. Awesome. You can use, one side note about Intruder is you can use up to 999 threads. You can't go to 1,000 or more. The Race the Web basically does like one thread for every single request. You're going to run into the same issues that you're going to run into with Burp, is if your computer or your network speed doesn't really support that much, it's just going to get a connection reset or it'll fail on that connection, which is fine because the goal of testing race conditions is you want to send a bunch of requests out. Doesn't matter if like all of them go through, because you're just trying to send as much data in as little time as possible to trigger that race condition. So that's just a side note of Burp Intruder. Continue. Yes, race was faster. Cool, that's the key. There's a few things that I actually want to do to add into Race the Web. Again, this is all based on if people are actually interested in this tool. If you go to GitHub, if you actually check it out, let me know online on Twitter or whatever if you are interested in this tool, and I'll keep developing it, because I want to help people find these issues. I want to help people to learn how to test for these things and make it a little bit easier, because this is not an easy thing to test. So a couple of things I want to add into the tool. Add a proxy option, so you could use it through Burp if you want, so that you can actually see all the requests that are going through if you want to modify or make any kind of changes on the fly. Up to you. I don't know how Burp's going to keep up with that, but that's fine. It'll give you the option. Even if you're in an environment where you have to go out through a proxy, this will help. So I'd like to add that in there. Should be pretty straightforward. I'm going to clean up the code base because honestly, I wrote this tool in the first place in like an hour on a trade ride home because I saw a really cool article on race conditions and vulnerabilities in race conditions, and I'll show that later. But I want to clean it up because right now it's just kind of a bit of a mess, but it'll get better, I promise. And I also want to actually write a Burp plugin. So what would be really cool is to make this a little bit easier for everyone that does web testing. Is I know everyone uses Burp. I use Burp all the time. That's my main tool when I'm doing web testing. So it would be great to have an easy way of passing a request into from Burp over to the tool. So I would like to do this. Again, this is all based on interest. If no one's using the tool, no one wants to use it, then why bother? But if everyone's interested in using it, then I would be happy to write these things in and make it easier for the community to use. So a few things to note, actually one main thing to note when you're testing for race conditions, a key thing you want to be aware of is denial of service attacks, because you're sending a bunch of traffic to an endpoint all at once. So if you're dealing with bug bounties, a lot of them have in their scope, they don't want things like denial of service attacks, and they don't want any kind of like any vulnerability testing tools that automatically send significant volumes of traffic. So be aware when if you're using this for bug bounty, that the scope might have this in there. Probably not the best place to test for race conditions. But if you're doing this for a client, if you're doing this on your own code, if you're developing and you want to see whether it's vulnerable, this will make it a lot easier. So just kind of be aware of that. And one other tip is check for CRUD functionality. So CRUD stands for create, read, update, and delete. It's just database functionality. If you can find database functionality in an application, most web applications do, unless you're dealing with static files. That's where you're more likely to find race conditions. Oh, and just general good advice, if you're doing testing for race conditions or anything on the web, check with different permission levels. So there's actually the option in Race the Web to use pass your session ID, because there's going to be some cases where you're going to need to actually be authenticated to log in. You can also pass headers too. So if you have other cookies that you want to pass, you can pass it into the headers too. But check with different authentication and authorization levels. So next, let's talk about defense. Now, fair warning, I'm going to fly through this one a little bit more. I'm still doing okay for time, but there's a lot of technical details specific to certain technologies in here that is difficult to take in at one time. So again, these slides will be up later, and you're going to have all the details you need for implementing those things and like links to more information as well. So let's talk about defense now. The most effective way to prevent race conditions is locks. So the concept of a lock is locking a resource while you're using it, so nothing else can access that resource at the same time. It's great. First way you can do that is through at the application level. So looking at Python, I'm going to go through a couple different languages, but basically, your programming language should support a way of locking resources while you're using it from other resources accessing that resource. I said resource a lot there. If you're doing any kind of programming with shared resources, check your documentation of your language to see if it supports locking. This is the best way to actually prevent race conditions. So I'll show you in Python, there's a few different ways in the threading library. You can use the lock function, you can use reentrant lock, you can use condition semaphore. You can use a queue. It's a different concept, a different way of actually handling shared resources. Basically works by handing off the resource, handing off the resource so only one person's accessing it at a time. I'll go into more detail with that in Go later, because it does a similar thing. And there's some more information there. So again, slides up later. You can look at this on your own. If you're using Python, seriously look at using this. If you're using the threading library, use the lock function as well, because or the lock class with the acquire function, because it's going to save your butt. Python, there's a fix. So remember the code earlier. This is how you would fix it. So if you look at the bottom, no, not at the bottom, the top function, increment thread, there's the lock.acquire and the lock.release. Those are the key parts, because it locks that resource while it's using it. So no other threads can access that resource at the same time. That's the key part here. So if you're looking at Python, this is the fix from the earlier code. And let's take a look in Go. Go has a mutual exclusion library with lock and unlock, which is what you want. And it also has a read-write mutex. Mutex means mutual exclusion. So it allows you to be a little bit more fine-grained with the locking, where you can do just read locks or read and write locks. And there's a link to the documentation. And this is kind of an idiom or an idea in Go that is very key to the language. It's the idea that to do not communicate by sharing memory, instead share memory by communicating. You have to think about it and say it a few times to really understand it, but what that basically means is that don't use shared resources, instead pass resources around. So don't use shared resources, pass resources around instead. This is a key concept to Go, and you can use that in a function, or it's a concept called channels. So it's a way of passing in. If you think about it like a stream, you can, if you have one worker up on the top of the stream, the worker is downstream listening for things that are dropped into there. You drop a resource in there, pass down the stream to the other side, it picks it up. There's only ever one person using that resource at a time. It's a different way of thinking about using resources. It's not necessarily having them all access the same resources at the same time. Instead, they're sharing that resource across, so only one is accessing it at a time. So Go has this concept. Python kind of has it with queues. Your language may support it as well. It's just a different way of thinking about using shared resources. And there's a fix for Go. You can look at it later, but basically it adds a lock at the bottom. And really kind of key to Go is the defer function. If you look at the defer function at the increment, sorry, the defer method or function in the increment function, it's a function a lot. What it, oh, great. Ready.
He's my colleague too, so we drink.
Thanks, buddy. Cheers.
Cheers.
Woo! Oh. Thanks, Patrick. That doesn't slow me down. I don't know what will. So, Go. If you look at the increment function, it uses a call called defer. What defer does is it basically makes sure that, in this case, it does the unlock function. Defer is used whenever you exit this function here, increment, or whatever function it's used in, whatever the parent scope is. Before that happens, before you exit that function, it will always, 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 always run whatever is beside defer. So if you put it in main, wherever you put it, before the program closes, before whatever its parent function is closes, it will always run this. So even if the system crash or like the console crash, it will do its very best to make sure that that runs. So in this case, it prevents that resource from actually being locked from other threads that are going to access it if for some reason that function closes early. So the fix is basically to do lock and unlock, and this is just a better way of doing it in Go. Let's move on to the next. PHP. Now, PHP is an interesting one. Because it's not built to really do concurrent programming, there's no real concept or way to fix this built into the language. Just another reason not to use PHP if you can avoid it. You could, I'm sorry for everyone here that likes PHP. It's useful, it has its uses, but if you're dealing with race conditions, it's tough. So to start, you could compile PHP with the enable sysvsem flag. So if you're recompiling PHP, what this does is it enables the concept of using semaphores in the language. A semaphore, using a semaphore, you can basically lock a single thread or a function to a single thread and allow only one thread to run that function at a time. So that's essentially the same thing that a lock does with multiple threads. But the downside of this is it's not supported everywhere. You can't necessarily use that flag or with PHP on some hosting providers, for example. In a distributed environment, you can't control the threads on another application through PHP, so it's not really useful there. And it's just in a shared environment, you may not actually be able to recompile PHP. So if you're using a hosting provider, you're given a specific version of PHP that you have to use. You can't necessarily recompile it and use your own version. So not ideal. You're pretty much stuck doing this at the database level or the file level. I'm going to get into a little bit more detail on that later, but ultimately PHP is not that great for this. If you do know of another way, please let me know, and I would be happy to update these in the slides because I want people to be able to fix this. But PHP is a little bit trickier. So I'm going to offer you a few other ways to prevent this, not only just at the application level. Next, let's look at the database level. For this to work, the database must be ACID compliant. What does that mean? Not Ninja Turtles. It means atomicity, consistency, isolation, and durability. Everyone here can read, so you can read this if you want. But those are basically different concepts that make sure that your data remains safe while you're using the database. The key point here is isolation. So in isolation transactions, when you're doing a transaction, that means you start the transaction, everything in there in that transaction is all kind of done at once. That's atomicity. But the key here is in isolation, it means that when you do a transaction in the database, that transaction is not going to affect other transactions that are happening. So there's different ways you can actually tweak that. So if you look at isolation, highest level that you can do is serializable. I'm gonna have to fly through this. I got 5 minutes. So serializable basically means you do transactions one after another. You can't really do things concurrently, but that prevents any kind of race conditions because you're not actually modifying that resource or doing anything to that resource at the same time. There's repeatable read as well. It's close. It kind of works more on the read level, like it allows you to do reads a little consistently, but updates and stuff, it's a little bit iffy in. So let's move on. Serializable is the best here, but be prepared to retry often, because if you're doing serializable and you're trying to put a transaction through, you're going to get an error back from the database, and you're going to have to retry that transaction until it's ready to actually accept it. So downside is that slows things down. So it's not ideal. It's going to for sure prevent race conditions when you're accessing those shared resources, but it's not the greatest for the business, and it's not necessarily the fastest. So you have a small little application that like 2 people are using, then go ahead and use serializable. It's probably the best way to go, but it may not be realistic for you. I'm not going to go through this in too much detail, but MySQL has a way of doing it. If you use InnoDB database engine, it provides full ACID compliance, so it has the capabilities for this. You can set serializable. Yeah, keep going. And here's different ways of setting serializable transactions in MySQL. So if you're actually using MySQL database, take a look at this. This will be useful for you. Postgres is actually pretty good. It has serializable built in. The default read committed is actually also pretty good. It allows you to read, so it kind of locks on updates as well, but it allows you to read the latest committed data, so the most up-to-date, while still allowing other things to happen at the same time. So it's actually okay, but it's not like perfect, but it's a good compromise between serializable and not serializable. So there's different ways of setting it. You can read on for more information. Going to keep going. These are just different ways of setting it in Postgres. So let's take a look at what a realistic compromise looks like when you're doing when you need to have database transaction isolation. In most cases, you're just going to do your best to optimize the queries, because if you're going to, all those examples that I showed before was reading data from the database, pulling it down, doing something locally, and then incrementing it in the database. If you don't necessarily need to do a whole lot of things locally, you can do it in one go. You can actually just increment the value in the database, and that one single shot at it is much better than it leaves less chance of that data changing mid database transaction. ORM, so object relation mapper, is basically a concept in programming where if you have a programming language, you have an ORM that takes care of a lot of the database stuff for you. Typically, databases are used what's known as pessimistic locking. So it's assuming the worst when you're using the database. So it's assuming that you're going to overwrite data, you're going to have a race condition, you're going to access shared resources at the same time, and so it locks it a little more aggressively. If you use an ORM, a lot of them come with what's known as optimistic locking. So it knows the context of how you're accessing the database, and so it does a little bit smarter. It's a little bit smarter in the way that it locks the data. So that's, if you check the documentation for your ORM, look for optimistic locking because that helps. Read committed, I mentioned this earlier. It's what Postgres does by default. It's not serializable, but it's pretty close. It's actually pretty good. Mongo, I mean, if you're using Mongo, good luck to you. It's a NoSQL database. It's got atomicity built in pretty well, but it doesn't really have the concept of transactions, so you can't really have isolated transactions. So you can use the isolated operator, which basically allows you to lock the database or lock the documents as you're writing to them. So it's pretty close, but it's not truly the same thing as an isolated transaction. So Mongo, that's the best you're going to get, and it doesn't work on sharded clusters. Here's an example of how to use it. Last one, looking at file level locks. Not going to go into too much detail here, but if you can lock shared resources if you're sharing file resources. There's built-in native methods in Windows. There's built-in native methods in Unix, and there's FCNTL is file control. So those are different built-in ways, but there's a lot of, the downside with this is Unix, the Unix methods are actually pretty finicky in a lot of ways, and there's a blog post here on those different gotchas that you can get with those. So if you're using them, I would highly recommend reading that resource before you do that, because it'll give you a lot of, you won't make assumptions about how you're using them that are going to be wrong. Best way to do it is to use a lock file. This is a lot of, if you're using like Dropbox, you're using even like Microsoft Word, it has that temp file with the like squiggly line before. This is what it is. It's a lock file. So it's basically saying this resource is being used right now. It's being written to. while this lock file exists, don't write to that resource. So it's a bit of a workaround, but it's probably the best way to implement file locks, especially on Unix when you have those native functions. So if you're building an application where you need to access files at the same time, take a look at file locks. It's probably the best way to get around it. Yeah. So don't overdo it. Realistically, you want to avoid locking hell. Don't share resources if you don't have to. I'm going to give you a few best practices in the next couple slides, but you can get into the case where the worst case scenario with locking is you can get a deadlock. If you're not actually unlocking a resource, or if something crashes and the resource doesn't unlock, nothing else can access that resource, and that's called a deadlock. So avoid those things by trying to do some best practices to avoid it. Some best practices. Ensure your database can keep up. So the database is a remote resource that introduces latency. So when you're accessing shared resources and there's latency between it, that can introduce cases where there's a race condition. Because that's the slowest point between the application and the database, you want to try to optimize that as much as you can. So these suggestions here are, this is like defense in depth. It's not a panacea. Like it's not the best, it's not going to solve everything, but these suggestions are things that you can implement on top of other things that you're doing to prevent race conditions. So your database, don't skimp on getting like the lowest micro level of AWS databases. It might be worth updating, like going up to a higher tier to make sure it keeps up, or even better, do it on the same network. So if you have an AWS resource, use an AWS database as well. So keeping them on the same resource reduces the latency, and it helps prevent those cases, those edge cases where you're going to get a race condition. Similar idea, fetch data only right as you need it. It's whether that's in a database, remote key store, whether that's locally in a file or remotely in a file, whatever. If you reduce the amount of time that you're spent pulling data and processing it, that data is getting stale. The more you can reduce that, the better. Again, this isn't the complete solution, but it's more defense in depth. So add this to your other solutions as well. And interesting, this is actually kind of an interesting notion of way of preventing this, C-sharp tokens. The reason is you can't automate a bunch of requests if they require a unique token every time. So C-sharp tokens don't prevent race conditions. They don't actually remove the vulnerability itself, but they really do prevent attackers from exploiting them, especially when you're dealing with them in a web application. So it makes it harder for attackers to actually make a bunch of requests to that endpoint if there's a different C-sharp token every single time. And C-sharp tokens in general are a good idea, so I hope you're all doing C-sharp tokens. Do it even for non-sensitive actions, yes. And really cool, if you're an attacker and you find a C-sharp vulnerability, take a look at it. You might actually be able to leverage that into a race condition. If they didn't do a C-sharp check, they might not be doing shared resource checking. So you might be able to turn that low vulnerability, low impact, into higher critical. You never know, worth a shot, try it. You never know what'll happen. So here's some further reading. Thanks to all these people that have written up some really good stuff on this. I believe the first one up there is actually the thing that introduced me to race conditions as like a serious issue. I've been aware of them like as the bane of my existence as a programmer, but I never thought of them as a vulnerability. And so that top one's really good information on that. Here's a bunch more reading if you want to do some further reading. Even the Web Applications Hackers Handbook mentions it in some part. There's some other talks, and there's the OWASP link at the bottom. So if you're interested in learning more, check those out. And now that you've got another tool in your tool belt, you have knowledge of what a race condition is, what the vulnerability is, and you have a tool to actually test for it and erase the web. So now go forth and erase the web. Thank you very much. Is there any questions before everyone gets up and leaves? Is there any questions that you have for me? Also know that afterwards, I think I'm pretty approachable. Come up to me and ask me questions anytime. I'd be happy to share and talk about it with you. Thank you.